All right, let's see how long this takes us run through. Hopefully you guys can hear this. We're going to run through these slides. Some of them will make sense, some of them won't. We'll try and be concise. Hopefully this video adds to your understanding, in addition to the understanding you've had from watching the videos already on AP Classroom. So again, some of this is great, some of it's not, and I'll let you know as we go through. Hopefully you follow along. And again, you can stop this video, take some notes, and then restart it. No big deal. Hopefully you've got all this and it makes sense. So, all right. Short version, energy can't be destroyed. You guys understand that hopefully fairly easily. Energy is always and should always be accountable. You can never just, oh, it disappeared. Okay, moving on. Look at that, same thing. So we talked about this briefly when we talked about the equation sheet you are given. Kinetic energy is K. You'll see me use kinetic energy as KE. To me, it makes more sense. It's also what I have been using. They will not count off on the AP exam if you use KE instead of K. Just understand it's a little different. Also, the same with potential energy is known as U. And then internal energy is E internal. Won't be very much, but the idea is this is energy that you either lost to friction, lost to heat, something. Okay, and again, this could be the total energy as well, depending on the situation. So we'll hopefully talk about that as we go through. Fancy energy. Oh my God, I love this slide. They did so great. Whiz bang things, maybe. Okay, cool. As you can see, I'm not a big fan of animations. So, short version, you should be able to measure it always, always, always. It is transferred from one thing to another. Mechanical process is main focus of physics. So, kinetic energy. Okay, so first, kinetic energy can be transferred into potential energy. Example, ball moving. The ball exerts a force on a spring. The spring now has potential energy elastic. You'll see that used. We'll talk about that in this chapter. And there's the verbiage. So an object cannot have potential energy. There can be potential energy in the system, the total thing. And that'll come in important. So if energy is transferred from one object to another, it has done work. And that's where our focus of this chapter is going to be. So example, we have a box, a system, an object. I use a crate all the time. Over the force, I'm exerting a force, making it appear to go to the left. That's the direction of motion. You can tell if work has been done is some force exerted over a certain distance. Okay? Note there at the bottom, a mechanical process is a process that involves motion. Okay? So if you don't have motion, most likely you do not have force or acceleration, so you should be able to calculate zero kinetic energy. Again, no force, no acceleration, no distance traveled, it didn't go anywhere. Okay? No work's been done. All right. Give you a second to read that. So, example, a box hitting another box. Box A exerts a force on box B. So, the positive work has been done. Okay? Energy is transferred from A, because A, in theory, would slow down, B would speed up. Positive work. Now, force exerted by A on B, again, if it didn't move, meaning, so point of application of the force didn't move in the direction. So it didn't move, no energy was transferred. No distance, no energy. No work done. All right, here's our fancy equation. Work equals force times distance. Ignore the incline for right now. Work is force times distance. That's it. A certain amount of force over a certain distance. That's all. Now, we have an issue. Example in the second half of that screen, if force is exerted perpendicular to the direction, no work is done. And one way to say this is your angle, theta, is 90 degrees. Hopefully you can understand cosine of 90 is 0. No work is done. Okay? The idea also, and this is an easy one to figure out, if you grab a box and you hold it at your chest height, You're just holding it, you haven't gone anywhere. No work has been done. Now, if I walk forward, if I'm walking forward holding the box at chest height, if there is no friction, no air resistance going opposite my travel, no work has been done. Because the force I'm fighting, just holding it, is just the force of gravity. But again, no distance. So, easiest example is that crate. You lift the crate from the ground to your chest height, work has been done. Because you exerted a force against the force of gravity, in this example, over a certain height, distance, you'd have done work. If you just stand there and hold it, you haven't traveled distance, no work. And here is your fancy equation. Work equals force times distance times the cosine of theta. Okay? Now, I like to make the note, d is the displacement of the point of the application of the force. And you'll see that on questions. Just make the note, d is the displacement of the point of application of that force. Meaning if you have other parts of the object that move, that's not where the work is done. All right, force does work when there's a displacement in its application. So in this case, we're putting force in x. Of course, we have gravity. There's our variables. Take a second, you could write those down. Again, it's not a hard equation, but it should be fairly simple. Cosine theta basically is the angle. In this case, if you notice, that should be F, force in the A direction. I just say force total, and you'll see me write that. Then we have force in the X direction, force in the Y direction. I split them up into X and Y because I use X, Y coordinate for pretty much everything I solve. So when they say force times A times cosine of theta is in the direction of travel, meaning the green, we're traveling to the left, A is in the force, that's the amount of force that helped us go in the direction D, okay? And you'll see me write this a lot. I use force in the X direction, or F net. And it basically, F net is the big force in red. F in the X direction would be my force in blue times the cosine of theta. So, force in the Y direction, because there is no distance in the Y direction, does no work. You'll see that question a lot. Okay, total force, there we go. And again, positive work, negative work. You'll see these angles. If the force is going in the direction of travel, the distance object, it's a positive work. Cool. If it's going against it, it would be negative work. Again, you have to use the negative sign. You should be able to see it. Positive work, negative work, negative work. Okay. And there's my generic equation. No work because the force is up. Moving on. All right, units for work are Newton, meter, and joule. Newton, meter, and joule. Work is joules, otherwise known as Newton meters. And hopefully that makes sense because you take force, Newton, time of distance, meter, Newton meter. Also called joules. 1 joule equals 1 Newton meter. Woohoo! I'm glad they put that down in writing. All right. So we have a displacement of 10. Work done is 8. Force times distance is 10. 8 times 10, 80 joules of work done. I love how they put that there because you don't really need to use that. All right, what if we put it on an angle? And hopefully you should be able to see, I'm going to use the cosine to find my x, the sine to find my y. 8 times 10 times the cosine of 30. And this should make sense. If you're pulling up at an angle, you're losing some of your force that you could be putting into the object. Okay? Now, what if I pull all up and the displacement still slides to 10 to the right? Doesn't really matter because you didn't do any force in the direction of travel, so no work. Again, cosine of 90. And if you notice, all of these are being measured from the distance traveled. I don't know if you guys see it. It's right there. It's kind of very, very faint, but anyway, moving on. And like this one, they should do one more. The force is in the opposite direction of the distance. We still have the force times the distance. We're still force times distance, cosine of 180, because the object is moving to the right, the force is to the left. Should say negative 80, or cosine of 180, because I start in the direction of travel and measure. All right. External forces, we'll talk about those. I'm not going to spend a lot of time there. Force, everything's good. Force of friction is lost. Hopefully you can see all those measurements. I'm not going to spend time going through each one. All right. Now remember, on the AP exam, you're going to put down the main force. That's what they want to see on a diagram. Do not put down the split force. Okay? This is your work. You can completely show it. And I will definitely recommend showing it like this for work. Just showing your work written out. Okay? So we split the force that was in a funny direction into all X and all Y. All X, all Y. Hey, force A, Y, force AX. Cool. It's also called force applied. One of the reasons why they use A. So, they break it down again. Force applied in the X, distance times cosine of theta. Because now we don't need an angle because we already split it. Hopefully that makes sense. And running through the numbers. Again, if you have questions, we're technically on slide 22. We can add it all up, and we should get a total of 60 newtons. Hopefully that makes sense, because the work done by your force applied minus the energy lost, or the work done by friction, gives you a total. Okay. Same idea applies for objects on an angle. Again, we're using the same force. 8 is our newtons of applied force. Our distance is still 10. We should still see the same amount of work. Except now we've lost a little bit more to friction and gravity. In this case, we just have... So, let me back up. We have the weight, and they use weight because it's force times acceleration. Gravity in the x direction. Hopefully you can see gravity in the x direction is going to pull, and in the y direction. I don't like how they printed that, but it's okay. I didn't catch that till just now. All right. Two objects in contact. So here we go. The right-hand side, you have an object, the force of your hand on a ball. Easy enough. So you have two objects in contact. Energy gained by the ball is equal to energy lost by the hand. Hopefully that makes sense. You guys have it in brain, so you're good. Stationary object, no kinetic energy, no movement. All right, external force. You guys, I'm not going to skip. I'm going to skip through this real quick. This is where you start seeing all your stuff compound, and which, sorry to say, it's going to get a little bit more complicated on this chapter, especially when they ask certain questions about objects moving in a circle or objects that have sped up. Example, on the left you have a final velocity of, so you went from velocity 1 to velocity 2 over a distance. They'll ask you to find acceleration. In most cases, your acceleration equals your velocity times distance over it. That gives you acceleration. You just dealt with this equation here. So this is a list of equations. Your kinetic energy is 1/2 mv squared. Okay? Hopefully you remember that. It's a physical science equation, so it should be fairly quick. I'm not going to spend going through all their bullets, and you'll see why. Work done on an object from rest. Hopefully there's another equation. I would say the work is the change in kinetic energy. And it gives you right there, work equals change in kinetic energy, kinetic final minus kinetic energy initial. This should make sense because I had a change in velocity. If I took an object and I sped it up, I have a change in velocity. Well, if I have a change in velocity, over a certain time, I have a change in acceleration. Well, if I change in acceleration, I have a change in force, which means I have a change in work. That is the left-hand side. The right-hand side, if I have a change in velocity, I have a change in kinetic energy. The reason we do this, and the reason we put this out there is, if you can find the object's velocity two different places, you can find the acceleration, or you can find the kinetic energy it had before and after. You can tell how much work was done on that object. This is the work energy theorem. You'll see that referenced a lot. Okay? I'm not going to go through this. We'll go through this in class. Hopefully you guys will see it fairly quickly. I'm not going to spend a lot of time going back and forth through the equations. And I'll do one in class to show you guys how to go all the way through it. But this is a long, drawn-out writing when it doesn't have to be. If you want to take the time, you can look at them as I go through them. But unfortunately, change in kinetic energy gives you a change in velocity. It still gives you a change in work. They get very long-winded for a simple fact of, oh wait, I can change the energy. I can find out the work that was done. All right, so let's skip to the next one. I'll skip this one too, because honestly, work done on the system. Center of mass is fairly important. We'll talk about it. For most parts, up until I tell you differently, you're going to assume the kinetic energy is in the center of the ball or in the center of the mass. Just makes life easier. Here's your long drawn out equation. Your work net is your change in energy, which includes kinetic energy, potential energy, and any internal energy. And that should make sense, because if you start in the middle, my total energy total, is made up of my movement, of my stored energy, of my internal energy. And again, my internal energy could be just the way my arrangement of my atoms. All right. We'll talk about cases where energy is transferred and can be converted. And that's a long drawn out problem I will go through later. Again, work done by a constant force. Constant force, force over distance. That's all it is. This is the graphical representation where you sit there and say, if you do 15, you need to be able to and use your graphs to find out the amount of work done. I am not a fan of graphing, but it has proven useful. Example, that's a constant force times a distance, okay? Now, a varying force, an increasing force. Hopefully you see the triangle is because you're going to use it. Oh wait, the area of a triangle, 1/2 times the base times the height. Look at that, 1/2 times the base times the height gets an area of, here's where I'm going to leave it, because we're going to do line displacement, okay? Once you get into higher level physics, you'll actually hopefully find integrals and using differential equations to find the area under a sine wave or a varying wave or a polynomial wave. Ain't gonna happen here. But again, displacement, if you notice, we went from -5 to 15, so we went up 10. They split it up where this area and this area is calculated, and that's your total because you had a negative and a positive. Is your total energy. Honestly, you'll see this angle going the other way, and that's actually more possible. Example, you had a -5 force, and then you had a 15 force, so basically you either were on a bungee cord, or you decided to change your mind when you hit 0 and push the other way. So, and here is your varying force, which I am not a fan of. This one, if you see it on the exam, they'll give you the areas of these. It will not be like this and you have to calculate it. They will give you the areas. Just understand, anything below the line would be negative, above the line is a positive. That gives you your work. All right, springs. I'm not going to go through too much because you have the equation. Slope of the line is equal to the force times the distance times the spring constant. Spring constant is basically your value that a spring is going to stretch and the force that's required to go over that inch. Okay? So if you, spring constant, if you smash it 1 meter, granted you can't smash a meter, got it. This is the force it's going to take to do that. That is your spring constant. Okay. Likewise, you can stretch it a meter too. Whoa. Hooke's law, you won't see too many questions about Hooke's law, hopefully. Force of the spring is equal to K times X, spring constant times the absolute value of X. Honestly, they're looking for the force that's required to make that spring move. Just understand your negative is compression, your positive will be tension. But again, if you understand the way the spring is moving, you can measure it, you're good to go. All right, Hooke's law. Area under a triangle. Still finding the slope, and we still come up with the same equation. Work is 1/2 times F times X. Still equals 1/2 times KX squared. It's a spring constant. Again, refer back to your equation sheet. You should be good to go. And I'm going to, because I'm not going to go through that one. I have way too many slides for simple concepts. Conservation of force. And spring force is conserved. It goes back to its original point. Friction is non-conservative. Got it. Because you build up heat. And we'll stop with potential energy. The idea is, this idea is your simple matter of rubber ball. This is one of those ones that compresses. It gains energy to the system. You're good to go. All right, that is way too many slides in way too many minutes. So if you have questions, hopefully we'll answer some of these in class and we'll go from there. See you in a few.